The special theory of relativity, introduced by Albert Einstein in 1905, stands as one of the most revolutionary ideas in the entire history of science. It fundamentally reshaped our understanding of space, time, motion, and energy, challenging centuries-old Newtonian concepts. In this video, we'll delve into the core tenets of the theory, explore its profound implications, and examine how it was first rigorously confirmed through real scientific experiments. The theory itself is elegantly built upon two powerful and seemingly simple principles that have far-reaching consequences. The first principle, known as the principle of relativity, states that the laws of physics are precisely the same for all observers moving at a constant speed in a straight line. This implies there is no absolute or privileged state of rest in the universe. All uniform motion is relative. Whether you're gliding smoothly in a high-speed train or standing still on a quiet street, the fundamental laws of nature operate identically. The second principle is truly extraordinary and counterintuitive. The speed of light in a vacuum is always the same for all observers. This constant speed, approximately 300,000 kilometers per second, is a universal speed limit, an unbreakable barrier in the cosmos. From these two seemingly simple principles, profound and mind-bending consequences naturally emerge, challenging our everyday intuition. One of the most famous is time dilation, the phenomenon where time itself appears to pass more slowly for an object the faster it moves relative to an observer. Imagine traveling close to the speed of light. Minutes might tick by for you, while years, even decades, could pass on Earth. This remarkable effect has been verified countless times with incredible precision, particularly with modern atomic clocks. However, even before the advent of these highly accurate devices, scientists were already actively searching for experimental evidence of relativity. Another striking prediction is length contraction, where objects moving at speeds approaching that of light appear shorter along their direction of motion. This contraction is imperceptible at everyday speeds. It only becomes significant and measurable when objects approach the immense velocity of light. Einstein also unveiled the profound and fundamental connection between mass and energy through his universally recognized equation, E equals mc squared. This equation tells us that mass can be directly converted into energy, and conversely, energy into mass. It reveals that even minuscule amounts of mass contain an incredible, concentrated amount of energy. This fundamental principle explains why stars shine with such brilliance and why nuclear reactions release such immense power. But how did scientists first manage to confirm that Einstein's revolutionary theory was indeed correct? The first truly successful and widely accepted experimental confirmation arrived just 3 years after Einstein published his groundbreaking theory. In 1908, the German physicist Alfred Bucherer performed a groundbreaking experiment involving fast-moving electrons. At that time, scientists already understood that the apparent mass of an electron seemed to change when it moved at high speeds. However, different prevailing theories offered conflicting predictions about precisely how this mass should change. Some experimental results even appeared to contradict Einstein's ideas, leading to considerable skepticism within the scientific community. Bucherer meticulously designed a more precise and sophisticated experiment using charged particles moving through carefully controlled electric and magnetic fields. By carefully measuring how these electrons curved as they moved at high speeds, he could accurately determine how their mass was changing. The result was striking and unambiguous. The electrons' behavior matched Einstein's predictions perfectly, providing crucial validation. Bucherer's experiment provided the first clear, convincing evidence that relativistic mass increase is a real phenomenon. It demonstrated that the special theory of relativity accurately describes the behavior of matter at high speeds, marking a significant turning point in physics. Since then, countless experiments have confirmed relativity with ever-increasing precision and across diverse phenomena. One of the most dramatic and compelling examples involves muons, unstable subatomic particles created high in Earth's upper atmosphere. Muons decay extremely quickly and, according to classical physics, should disappear long before reaching the ground. However, because they travel near the speed of light, their internal clocks run significantly slower due to time dilation. This relativistic effect allows them to survive long enough to be detected at Earth's surface, exactly as Einstein predicted. Particle accelerators provide even stronger and more direct evidence of special relativity. At facilities like CERN, particles are propelled to speeds incredibly close to the speed of light, pushing the boundaries of physics. Their mass dramatically increases, their lifetime stretch, and their motion precisely follows Einstein's equations with astonishing accuracy. Engineers and physicists rely on relativity constantly to design, operate, and make these complex machines function effectively. Relativity also plays an absolutely essential role in modern technology, impacting our daily lives in profound ways. The Global Positioning System, or GPS, is a prime example. GPS satellites orbit Earth at extremely high speeds and experience different gravitational conditions than on the surface. As a direct consequence, their onboard atomic clocks run at slightly different rates compared to clocks on Earth. Without meticulously applying both special and general relativity, your GPS location would drift by several kilometers each and every day. Relativity is what keeps your navigation accurate and reliable, enabling countless applications from mapping to logistics. All of these experiments unequivocally demonstrate that space and time are not fixed, rigid, or absolute entities. Instead, they are elastic, interconnected, and profoundly influenced by motion and gravity. Einstein's special theory of relativity opened the door to modern physics and laid the essential foundation for the general theory of relativity. This later theory would soon reshape our understanding of gravity itself, presenting it not as a force, but as a curvature of space-time. Special relativity shows us that the universe is far more dynamic and surprising than our everyday experience suggests. It is a place where time stretches, lengths shrink, and energy and mass flow seamlessly into one another, revealing a deeper reality. Thank you for watching this exploration of Einstein's special theory of relativity.